Hi, everyone. In this video, we're going to be talking about conjugate acid-base pairs. Now, before we can explain what that means, let's define acids and bases according to a different set of definitions. Bronsted and Lowry defined acids and bases based on hydrogen ions. And so according to the Bronsted-Lowry theory, an acid is a substance that donates H+, just like Arrhenius. But Bronsted and Lowry defined a base as anything that accepts H+. And so the reason for this definition is that hydrogen ions don't really exist on their own. They're too reactive. So an acid spits off H+, but whatever comes into contact with that H+ absorbs it. And so bases are the things that absorb the H+ in solution. And so in order to absorb H+, the base has to have a lone pair of electrons that can form a new bond to the hydrogen ion or the proton. So here's an example. So you have HA as your acid, and this is going to give off the hydrogen. And B here is your base. And this lone pair on the base is going to come over and grab that hydrogen. And this bond between the hydrogen and the acid is going to break. And those electrons from this bond are going to go onto the A. And so what you end up with is the anion with a lone pair and a negative charge. And you have the base now bonded to the hydrogen atom, and it's positively charged. So your acid gives off the hydrogen and your base absorbed the hydrogen. So once again, the electrons from the bond between the hydrogen and the acid stay on the anion, and the lone pair from the base forms the new bond to the hydrogen. So the base gains H+, and the acid loses H+. Now, let's take a look at some common Bronsted-Lowry bases. Similar to Arrhenius bases, anything with an OH minus is a base. So sodium hydroxide, potassium hydroxide, magnesium or calcium hydroxide. These all have OH minus, and so they're good bases. Now, two things that can act as bases, according to Bronsted-Lowry, are ammonia and water. They both have a lone pair, and so they are able to absorb that extra hydrogen if the situation arises. Now, a couple new terms. Once the acid has lost its hydrogen, we refer to it as the conjugate base. And once the base has absorbed the hydrogen, we refer to it as the conjugate acid. Now, oftentimes acid-base reactions are reversible, meaning the acid can give its hydrogen to the base, but then maybe the conjugate base will steal the hydrogen and you'll go back to where you started from. And so this is an equilibrium where they're basically playing tennis with the hydrogen ion. And so if you're thinking about the reaction going backwards, this HB here has the hydrogen. And so it would act as the acid if it was going to give it away. So that's why we call it the conjugate acid. And the A minus now has the lone pair and is able to accept the hydrogen if we're going backwards. And so that's why we would refer to it as the conjugate base. And so these are referred to as conjugate acid base pairs. So the acid and the conjugate base are a acid base pair, and the base and the conjugate acid are a pair. Let's look at a specific example here. So HBr is an acid. And in this case, water is going to act as the base. And so the HBr is going to give its hydrogen to the water. And so it becomes Br minus, and the water picks up the hydrogen to become H3O plus. The Br minus is the conjugate base, The H3O plus is the conjugate acid. And something that's important to note here is that the net charge is the same on the product side and the reactant side. So on the reactant side, there's no charges. And on the product side, there's a minus charge and a plus charge, which overall makes a zero charge. And so the charges have to be the same on the left side as the right side. So let's take a look at another situation where water acts as the base. So in the reaction of hydrogen chloride and water, the HCl is going to give off its hydrogen. And so it's going to act as the acid. And water is going to act as the base. And so HCl gives its hydrogen to water. So water becomes H3O plus, which is known as hydronium. And this chlorine is now chloride. Okay? And so this H3O plus would be the conjugate acid. And the Cl minus would be the conjugate base. And so this is just an example where water acts as the base and absorbs the extra hydrogen. Now let's take a look at a scenario where water acts as the acid. So in the reaction of ammonia and water, the ammonia acts as the base and water acts as the acid. So water is going to give one of its hydrogens to ammonia. And so ammonia picked up the extra hydrogen. So this is our conjugate acid. And the OH minus is our conjugate base. So this is just an example where water behaved like an acid, as opposed to the previous example where water behaved as a base. So water can swing both ways. You can be an acid or a base, depending on the specific situation. So let's take a look at some characteristics of acids and bases. So according to the Arrhenius definition, acids produce hydrogen and bases produce hydroxide. According to the Bronsted-Lowry definition, acids give off H+, bases accept H+. Both of them are electrolytes. Acids are sour, bases are bitter and chalky. Let's do a study check. In each of the following equations, identify the acid and the base in the reactants. So in the first reaction here, we want to look and see who's giving off the hydrogen. And so it looks like here we have HNO3, but on the right side we have NO3 minus. So it looks like this is the species that gave away the hydrogen. So this is going to be the acid, and water is going to be acting as the base. And so water absorbed the extra hydrogen. And so we could refer to this as the conjugate acid. And this would be the conjugate base. Now, in the second scenario, we're once again looking to see who's giving away hydrogen. Acids give off hydrogen. And so I noticed there's an HF here. And on the right side, it's only F minus. So it looks like this was the acid, which means that this must be the base. And so the H2O absorbed the extra hydrogen and is now H3O plus. So this is the conjugate acid, and this is the conjugate base. So another study check. Identify each as an acid or a base. So a sour taste, well, that's going to be an acid. Produces OH minus, that's going to be a base. Chalky taste, once again, that's going to be a base. It's an electrolyte. Both acids and bases are electrolytes. and it produces H plus in aqueous solutions. That's going to be the acid. All right, another study check. Write the conjugate base for each of the following acids. So remember, the conjugate base is what an acid looks like after it lost the hydrogen. So in this case, if this gave away H plus, what would be remaining is Br minus. So that's going to be the conjugate base. All right, next one, H2S. If it loses an H plus, what we're going to be left with is HS minus. That's the conjugate base. And H2CO3, if it loses H plus, what remains is going to be HCO3 minus. So these are the conjugate bases of these acids. Now, the second part, they're asking us to write the conjugate acid for each of the following bases. So what do these look like when they absorb H plus? So if this picked up an H plus, it would be HNO3. The negative charge and the positive charge would cancel out, and so you'd just be neutral. Now, NH3. If this absorbed H plus, the NH3 would become NH4. And a neutral charge and a +1 charge is going to add up to a +1 charge. Remember, you got to make sure the charges, the total charges on the left side match the total charges on the right side. And the third one, if OH minus absorbed a hydrogen ion, that would be H2O. The minus and the plus cancel, and so we would just be neutral. So the flowchart for figuring out conjugate acid-base pairs is to always follow the H plus. The thing that loses H plus is the acid. The thing that gains H plus is the base. And once you've established that, you can figure out the conjugate acid-base pairs. So one more practice problem. Identify the conjugate acid-base pairs in the following reaction. So which of these two is the acid and which is the base? So we got to track the hydrogen. Here you'll notice we have HNO3, but on the right side, we only have NO3 minus. So it looks like this gave away the hydrogen. So this is going to be the acid, and this is going to be the base. And so this is our first acid-base pair. And over here, this is going to be the conjugate base. And then the base, when it absorbs the hydrogen, becomes the conjugate acid. And so these are our two conjugate acid-base pairs. Thanks for watching, and I will see you in the next video.